Welcome to Pop-Up Presentations. We've got a guest today. Juan Chong is going to give us a little bit of a thing into FRC batteries. I think this version of the motorcycle battery has been the battery that we use since at least 2001.
Yeah, I think so.
But we're still learning about it. There's still more to know. So,
Yes.
and it's what we're going to be using for the foreseeable future.
Unfortunately, yes.
So get into why that's unfortunate.
Yes. Yeah. Now I'll get into why that's unfortunate, and also like why this has why we're still using this battery. 20 years on. So yeah, my name is Juan. I am a motion sensors engineer at Meta, but my background is actually in electronics, power electronics, and high voltage switching, high current switching stuff. Batteries are kind of related to that. And I've been doing FRC for 16, 17 years, something like that. It's been a while. But yeah. So I guess to get started, things I'm going to go over, battery design. So like, what do the batteries look like inside? How do they work? I'm going to get into care and maintenance of the batteries. So we normally, on an FRC team, you don't really think about how you handle the batteries. You just kind of like put them in the robot, you take them out, put them on the charger, and that's probably the extent of what you're doing with them. We'll talk about why that may not be enough. Battery failure modes. So some of the ways in which the batteries can fail, some of the ways in which teams usually will break batteries, or, things that might lead to, lost matches, or maybe your robot dies on the field or something happens, right? We'll talk about that. And we'll talk about load testing. So how you're actually supposed to test the batteries. Some of the load testers, or some teams will usually load test the batteries at the beginning of the season and then not do it until the next season. Turns out that actually may not be enough to, make sure that you don't lose any matches. All right, so by and large, there are 3 different styles of lead acid batteries. And yes, I'm going to have to talk a little bit about chemistry, and it's going to be a little bit scary for a minute, but hang in there with me, Hey, and there's technically like Twitch chat right now, so I can actually make the, hang in there Twitch chat. It's not that scary reference. Oh, okay. Well, hang in there, YouTube. So yeah, by and large, lead acid batteries basically have to have an electrolyte. An electrolyte is, you can think of it kind of as essentially water with a salt of some sort in it, and typically some sort of mild acid. And you'll usually have 2 plates. There's a positive and negative plate for each battery cell. And battery manufacturers will stack a bunch of those plates, those cells together, to form what we know as a battery. Now you'll see here that there are the two battery types on the left and the right are, kind of liquid and gelled electrolytes. So they are literally liquid, like filled with the liquid, actually water, or the gel, which is kind of a water glycol mixed mostly so that it doesn't evaporate. And then there's this electrolyte in this absorptive glass mat. So this glass mat, this glass material, is actually impregnated with this electrolyte. And essentially the battery chemistry works out so that it can't like spill. It can't actually, for the most part, leak out. It's not really solid state either, right? Like technically there's still a little bit of gel, technically it's still kind of a liquid, but like it's a lot more resistant to leaking if you flip it over, if your robot flips over, if you accidentally run a drill through the battery, those types of things, it'll kind of prevent acid from spilling out of these things. And in FRC, we only use the one in the middle, the absorbed glass mat style batteries, for that specific reason, right? We want to make sure that if your robot flips over, if somebody accidentally does something that would damage the battery, those types of things, we don't start a fire, and we also don't cause a lot of harm. So, what does one of those batteries look like? Well, it's literally what it says on the box, right? Absorbed glass mat. So there are fiberglass sheets, fiberglass mats that are where the electrolyte is, kind of absorbed into it, in the name. And these glass mats are actually wrapped around the these two metal grids or electrodes, and the grids are made out of lead or something that is, or a metal that is, or an alloy that is mostly lead. What this does is, like I said, it forms a little cell, battery cell, and you'll see that they actually have a bunch of these kind of stacked together. In this case, wired in some in series, some in parallel. It'll depend on what the battery composition is, but for the most part, you require obviously all of the cells to maintain the voltage that we know and use. Now, you'll notice that like this, even in this drawing, the metal contacts, there's only a small metal contact on the top of the battery, and then these contacts are all kind of soldered or welded into, or probably stamped and formed into what turns out to be the battery terminals, and that's what we plug our robot into, right? This is another diagram from an interstate battery. The battery manufacturers will change the dimensions of the battery, and that will usually also change how you connect to the battery. So these have posts on it. These are batteries that are designed to be put in cars or on boats, that kind of thing. But we actually use a motorcycle battery, and that'll play into things a little bit once we start talking about some of the failure modes. At a very high level, the way that the battery works is there is, like I mentioned, an acid intermixed within the water, within the electrolyte, and you basically have two lead contacts, and during charging, what will happen is, I believe it's electrolysis will actually let me think about this. Essentially, what will happen is the water will become more acidic as you apply charge into the battery, and as you consume power from the battery, you pull power out of it. There's a chemical reaction inside of the battery that actually separates removes some of the acidity from the electrolyte. And whenever there's not enough acid left, well, your battery, at that point you don't have any more chemical to continue that reaction, so the battery is, discharged, right? As you, in order to recharge it, you apply charge to the battery, and that will actually kind of increase the acidity once again, and the cycle repeats, right? The way that they work. Now, like I mentioned earlier, AGM batteries are the only batteries used in FRC. There are many benefits to them. There are also lots of drawbacks. The benefits are that the battery is sealed, and it's considered non-spillable unless you do something like, I don't know, run a drill through it. And even then, nothing will typically leak out of them. You have to do really terrible things to actually have liquids come out of these batteries. We'll actually get to that. The batteries are typically pretty happy with, high discharge. So like, they're happy to be discharged pretty substantially. So you remove 50% of the energy stored in the battery, is what the industry considers as deeply discharged. And they're also really happy to accept a fast charge. So it actually doesn't really hurt them to apply 6 amps or whatever of charge to them. They're pretty happy to do that under most conditions. The batteries are, by and large, vibration and shock resistant, once again, with corner cases, with a couple exceptions. And they have a lower internal resistance than most other lead acid batteries, and that's important for efficiency. Some of the drawbacks, of course, you have to charge these batteries with a charger that's capable of AGM charging. So the charger has to be smart enough to be able to measure the battery understand what, how it's charging, how it's accepting that charge, and adjust what it's doing to fit the battery. If you don't do this, you can actually wind up overcharging the battery and permanently damaging it, which is one of the ways in which most teams actually damage their batteries. The charge, you have to maintain the charge on the battery in order to prevent damage. So if you don't charge the battery, so let's say you go to a competition and, yay, we're done for the day, pack everything up, go to your shop, leave everything in your shop for 2 weeks, come back, odds are that the battery that you used in your final match will probably not be good anymore, because you've now discharged the battery pretty substantially and you never actually recharged the battery or got it out of that zone where damage can occur. So in other words, leaving batteries deeply discharged is also bad. Well, I guess that was the next point. Now, like I mentioned earlier, overcharging the battery, and it usually happens when you use the wrong charger. If you use the wrong charger, you are very likely to also damage the batteries. I think some folks may have heard the term, the battery might cook, like literally the water inside of the battery boils off, and there's no more, once again, there is no electrolyte left for the chemical reaction to occur. So if you charge the battery too much, it will boil off that water, that liquid that's inside of it, and the battery's done. Because these are, sealed batteries, you actually can't refill them. So a wet cell battery, typically used in cars, you can actually just pop open the lid, take some distilled water, pour it in, refill that cavity with water, and the battery will work again, usually. Also, high temperature. So elevated temperature can have some benefits and drawbacks. This is kind of a weird one. The battery is happy to accept charge at a slightly elevated temperature. So keeping the battery at about 20 to 25 degrees Celsius is where it wants to be, which room temperature is usually 19, 20, 21 Celsius. However, if you try to charge the battery when the battery is warm or hot, you actually will, over just a few cycles, damage the battery, or at least reduce its lifespan. Now, in FRC, you might get 1 or 2 seasons out of a battery, and that's okay. That's pretty good. So this last one, that's why it's kind of like, it's a good thing to keep in mind. There are ways to manage it that I'll talk about later. Actually, any questions from the crowd up until here? Wait till the end? I don't know. Let's see. So, I guess a good thing to go over, and probably this is what folks came to see, is how do these batteries fail in FRC, right? So there are mechanical failures, or, chemical failures. There are a lot of things that can happen. So broken terminals actually happens quite a bit. So I mentioned earlier that essentially the way that these batteries work is there are a bunch of little cells inside of them, and those cells all have to be attached to typically a bus bar. If there's a lot of vibration, or if you drop the battery, those contacts and where everything is kind of connected together can crack or can break. So what'll happen is, if you take a multimeter, maybe you take a battery Beak, you measure your voltage, you might actually measure, 13.8 or whatever it is, 13.6, you might measure a good voltage. But as soon as you try to pull current from it, the internal resistance and internal heating of the battery will cause things to expand, and that crack will move. And suddenly you've lost, 0.2, 0.5 volts, right? Or a volt or whatever, depending on where the crack is. So the way that the motorcycle batteries work, instead of there being a big post like you see here that that's designed to bolt onto or to be clamped onto, the motorcycle batteries, the two, connectors that come out of the battery go directly to that bus bar. So if you bend it, or if you torque it, or if you lift the battery from the cables, or if you zip tie and over constrain the battery cable to try and get it inside of the robot perimeter, like I've seen certain teams do, that might actually lead to damage on the inside of the battery itself, and it might lead to failure. Unfortunately, on the field, this is actually a really hard failure to catch before matches. There are also a chance for positive and negative plate cracks. So I showed in an image earlier that inside of the battery there are these metal meshes, metal plates, and they just have a little tab coming off of them. Sometimes those tabs can crack. Sometimes the plate can also crack. So once again, also a big, another reason to just like not drop the batteries, right? At least the teams that I've worked with directly with in the past, what we've done is we've kept track of whether a battery was dropped or not. So if we were transporting the batteries, if we were, pulling them out of the robot, whatever, right? If somebody drops a battery, the procedure that we had in place was to immediately wrap electrical tape around the battery in some color and just write on it, dropped in this state. We didn't need to know who it was, whatever, right? It's just, hey, this battery was dropped, which meant we had to go back and do load testing on it just to make sure that the battery was still okay after the drop. Now, the other thing that can happen that I see a lot in FRC is not isolating the battery terminals. So the battery itself from mechanical vibration, excuse me. A lot of teams will actually take the battery, slot it into their robot, and it's a slot designed perfectly for the battery to fit, and the battery itself is essentially mechanically connected to the robot base. If you think about what happens on the robot as you're driving around, there's a lot of mechanical vibration, and then of course there's the shock aspect, right? You run into another robot, and now the battery is essentially also slamming into metal inside of that slot that you've put in the robot. Even adding a little bit of dampening, actually we've used a yoga mat, is more than enough to actually prevent a lot of this damage. We actually did find that I think we tested 25 batteries or so, some with the protective foam, some without, like basically half and half with, half without. And we actually saw that the batteries without the protective foam tended to have less stellar performance. Like all of them performed worse than the batteries that did have that protective foam. And you only need like half an inch maybe around the battery. It's not a lot that you need. I mentioned this earlier. The other big thing that teams do is they'll boil off the electrolyte. If a battery sits on a charger and the charger is not aware that it's connected to an AGM style battery, the charger will set voltages higher than what AGM batteries want. They also won't follow a profile that AGM batteries are designed to charge at. This will slowly heat the battery, and just over time, there's a valve, there's a valve inside of the battery to allow pressure to exit, right? So if there's a pressure differential, it will actually bleed off some of that pressure. What it bleeds off is typically water. So, once you run out of water, the battery is useless, right? Because there's no more electrolyte. The other thing that can happen a lot in FRC is not allowing the batteries to cool. So if you take the batteries out of the robot, you just played your match, take the batteries out of the robot, you connect it, and you immediately put it on the charger. I'm sure everybody who's dealt with the batteries after working with the robot has realized that like the batteries get hot, right? These batteries are designed to run at maybe ideally 25, 35 degrees Celsius. These batteries get hot. Then you're trying to put charge back into it. This just leads to more quickly boiling off the electrolyte, which reduces your battery capacity. The way that we handled it before was we actually had a FIFO, right? Literally a queue of batteries. And the battery comes out of the robot and you put it in the back of the queue. And as you know, the competition progresses, you pull one off of the front of the queue that's already nice and cool and it's ready and it's charged, plug it into the robot, and you continuously just, you know, rotate that. By the time the battery gets to the charging part of the queue, the battery's, you know, reasonably cool. Like it's pretty simple to handle. Um, the other one is loose battery terminals. So this one's kind of interesting. The If the battery terminals are loose, what can happen is the cable will actually heat up, right? Because of course you've got a loose connection, increased resistance, the cable will get hotter. But that heat also, you know, of course, some of it gets radiated into the air, right? By I guess it's some of the heat gets transferred by means of the air. The heat will also get transferred into the battery. The cells closest to the terminals will get a lot hotter. So you'll boil off the electrolyte of the battery of the on the glass mats or the cells nearest the terminals. Um, so, and because this isn't a wet battery where, you know, the electrolyte is kind of like everywhere, you'll wind up with a couple of cells that just can't charge anymore. So that'll overall decrease your battery capacity. That's what that leads to. The other one that affects a lot of FRC teams, and this is probably, it's hard to say which one's the worst, but sulfation is probably the top reason why these batteries run into issues. If you leave the batteries unattended between seasons and you don't leave them on a charger or you don't cycle them or do anything with them, you basically just, you know, leave them in the shop, whatever, for a couple of months, you'll wind up with something called sulfation. And sulfation basically means there are crystals that will form on the metal plates inside of the battery. If you've ever seen, and I've got a couple pictures of it, basically these crystals form and they prevent the electrolyte from contacting the metal, you know, the lead inside of the battery. Essentially creates a little barrier, kind of like how, you know, what happens when like copper is exposed to the air, right? You know, because it interacts with oxygen, copper will get kind of a sheen on it, and that's, you know, the oxide layer that forms on the surface of the metal. In this case, it's a byproduct of you know, it's a chemical byproduct of the chemical reaction. But yeah, basically, if you leave the batteries unattended for a couple of weeks, a couple of months, or in a very low charge state for a couple of weeks, a couple of months, basically you won't be able to recover the battery because it'll have this crystal coating on it inside, and sometimes outside, which is kind of odd. This is kind of what it looks like. If you've ever seen an old car battery, you've probably seen at least a little bit of this. You know, it's this, like I said, it's a crystal. If you look at it, it kind of looks like shaved ice, only don't eat it. I mean, it's 2024, unfortunately, I have to say that. Um, And yeah, just imagine, I couldn't find any good pictures of it, but imagine that basically this blue fuzzy stuff covering the metal plates, which is kind of not what you want in a battery. Um, like I mentioned, it happens slowly. It takes a couple of weeks, couple of months. Um, you know, depends on charge state. It depends on a bunch of other stuff, but you know, TLDR, it happens. There's two types. There's the permanent kind, which is basically you've got so much on there that like you can't break it apart. And there's, you know, reversible or soft sulfation. You can actually break apart and recover the battery essentially by using a desulfator, which is tough to say. This device basically pulses the battery voltage at pretty high voltages to purposely force the crystals to break apart. Don't try to do this manually. Don't just no, go to Amazon, buy one of a desulfator that is designed for AGM batteries, because if you use one for a standard, you know, wet cell lead acid battery, like, you will nuke the battery very quickly. Some chargers, actually, including the chargers that AndyMark sells, have this feature built into the charger. So every time that you plug in the battery, it will actually run a desulfation cycle, and to help prevent that buildup on the cells. We've actually used those chargers to recover batteries that were kind of on the edge. A battery that has this issue will actually look a lot like, so if you measure the voltage on the battery, the peak voltage, so like, the charger says, yep, you're charged or whatever, the peak voltage will look a little bit lower. Instead of it being 13.4, it'll be like 13.1, 13, 12.9, that type of thing. And of course, when you put it in the robot, like the charge will like disappear. As soon as you start driving the robot, suddenly your voltage will dip, and it won't be good. When I mentioned that, like, yeah, some chargers actually do this. So this is kind of like what the waveform looks like when you plug a battery into a charger like this. It'll actually like whack the battery at like 35 volts or something, 40 volts, but for like a couple microseconds, right? It's a very, very short pulse, but that's enough to create essentially cracks in the crystals that form on the surface. And that actually, because they're cracks, eventually the chemical process will reabsorb the crystals back into the electrolyte. But once again, you must use an AGM charger. You must use one, otherwise you will just destroy batteries. Now, this is kind of a change in this is kind of more like my opinion of where we are in FRC, but FRC batteries used to, like, the use cases for FRC batteries used to be more constant, right? With like DC, with brushed DC motors, with big heavier robots, that type of, like, it just it used to be very difficult to build a drivetrain that could quickly change direction, or like omnidirectional drive wasn't a thing. You had these slow mechanisms, all this stuff, right? The battery drain looked a lot more constant, a lot more like less spiky, right? Nowadays, with brushless motors, with swerve, with all, with every motor controller having some sort of, control loop in it and requiring a lot of switching, if you like suddenly change directions on a swerve drive on a, competition FRC robot that weighs the full 120 pounds, I mean, you can pull 120, 140, 180 amps out of a battery, instantaneously for, I don't know, a couple milliseconds, tens of milliseconds, right? That looks a lot more like starting a car. So now what starts to matter more is, instead of the like total capacity of the battery, actually what starts to matter is cold cranking amps, like essentially how many car cranks you can get out of a battery, or in this case, motorcycle cranks can you get out of a battery before it just, before you're at a voltage where you can't use it anymore. And that is important to think about when you load test the batteries. So previously, because the loads were pretty stable, pretty consistent, you could get away with load testing a battery at, let's say 10 amps, essentially pulling 10 amps, 20 amps out of a battery, and then just kind of seeing how the voltage changed over time. Not anymore. You actually need batteries to perform well at, when, I guess, on the robot. So whenever you're pulling lots of current out of them. The best way to do this is actually with a carbon pile load tester. And when I say you should load test the batteries, I don't mean once a season. I mean before you put it in the robot. These style of load testers can put 300 amps, 500 amps on a battery for a second or two, which it seems like a lot. It feels like you're wasting a lot of energy, but doing it this way will actually uncover a lot of the issues that I mentioned earlier, the cracks in the conductors and the things inside of the battery, cracks on the plates, it'll find out whether there are any weak connections, anything else going on inside of the battery. In addition to this, I also recommend using an infrared camera. So believe it or not, a lot of the issues related to batteries, battery reliability, battery failure, you can detect them using like a camera. If there's a failed cell or there's a couple failed cells, you suspect that something's going on in the battery, you can literally use the IR camera to look at it after you've been drawing current out of it, and you can see, is there a spot in the battery that's cold, hot? Is the battery consistently warm? Are the cables the same temperature, right? You got to have positive and negative, right? So are both of the cables the same temperature? If they're, if one's considerably hotter than the other, you probably have a loose connection, right? Same thing with the motors, same thing with the motor controllers. A thermal camera actually helps debug. It can debug so much stuff. Super highly recommended. There's also another discussion. Maybe we'll save this one for later, but there's a discussion on what happens, or why would we want to use larger gauge wire? Why you want to use connectors, larger connectors, that type of thing. Actually, that would be another good one to follow up on. If y'all are up for it, because I didn't prepare this as much as the battery side. There's a whole other thing on the SB, what is it, the SB50s? Yeah, the SB50s, which is what's normally used in FRC, they're designed to, I think it's 40 amps continuously. Yeah, we don't do that. SB120s are designed to carry, I think, 180 or 100 amps continuously. There's RMS and peak, and how much are we, it's that whole thing. So maybe we talk about that. Maybe I come back in a couple of weeks and we talk about it. I guess any other questions on batteries? Does anybody have any questions? Go for it. Yeah.
So we've noticed that if we heat up a battery, it has lower resistance and performs better during a match.
Mm-hmm.
If we heat it up beforehand. Does that? But you're saying that damages the batteries?
Mm-hmm. Yep. That'll eat into the battery's lifetime. Because. Oh yes. One of the students mentioned that they've noticed that when the team heats up the batteries, that the batteries will seem to perform a little bit better. Yes, that is the case, right? The chemical reaction is happier to take place at slightly elevated temperatures, 25, 30 degrees Celsius, that type of thing. However, there's a trade-off, right? It's what we talked about with the electrolyte, and it has more to do with the lifetime of the battery, the lifespan of the battery. If you had a data center and you had to have a bunch of batteries on standby in case the power goes out, you probably want those batteries to last, 3 to 5 years. For us in FRC, if you get a season out of them, then cool, right? Maybe 2 seasons, have the practice bot set and the competition bot set. But yeah, it has to do more with you eat into the lifetime of the battery, not the performance of the battery. Yeah. We'll go. Yeah.
So you were talking about load testing.
Mm-hmm.
So I saw that you said you shouldn't load test just once a season. You should load test before you put on the robot. So
Mm-hmm.
does that mean how often is that specifically load testing? Would that be multiple times through the competition season? Would that be multiple times at one event? Or can you just break that down a little bit more? How often we should load testing?
Yeah. So the question is, how often load testing should occur? Should it be, a couple times a season? Maybe before each event? My recommendation is actually to load test before every match. Before keep a load tester on the cart know how to load test, teach your drive team how to load test, and test the battery before you put it in the robot. The reason for that is, I don't think it's the biggest reason. There are multiple reasons, I guess. You want to catch any damage during transportation, right? Did somebody drop it off the cart and nobody noticed and just put it back on the cart? Probably don't want to put that on your competition robot, right? Did anything get damaged while it was transported? Did something get loose? Did a cable get loose? All you can identify all of those things. Something we used to do as well is we used to have a space on the battery where you would Sharpie what the last measurement was, or kind of keep a log of the measurements on that load tester. And then at the end of the competition, just take an alcohol wipe and wipe it all away. It's fine. It's just you need it to be permanent enough to not get wiped away, so you don't want to use wet erase mark or whatever. But you want to keep track of it, right? If you see that a battery was testing at 300, 400 amps, and then all of a sudden it tests at 100, something really bad just happened to that battery, and you definitely don't want to run it in a match. Yeah.
What was the tool you were recommending for load testing? Because the first one doesn't work anymore.
I can put a link to it, but the question was what was the tool or what is the load tester that I recommend? The easiest way to go and get one is to go to Harbor Freight. Harbor Freight sells these things for about $15-$20. You can buy them on Amazon if you search for carbon pile tester. It literally is exactly what it says. It is just a couple of sheets of carbon that they basically attached contacts to, and they just use the carbon's resistance to high resistance, but also ability to absorb a lot of heat as the load tester. Some load testers for the smaller capacity ones are just literally a switch with a wire inside, and then they just have a little multimeter attached to it, and that's it. They're super, super simple. The one that you saw in the pictures and the one that I have here, I just remove the alligator clips from it and put an SB50 on it. It's pretty simple. So yeah, your battery problems can potentially go away for $15 or $20 if you just go get one from Harbor Freight.
Well, those can that doesn't get rid of the problem.
It doesn't get rid of the problem, but you're detecting the problem before you put it in a match, on the robot or run a match with it. That problem can definitely go away for $15 or $20. Yeah.
So, when we're practicing, obviously, doing practice matches and stuff, obviously that's a different situation than match play and event play. Could you just, I think you've talked a lot about, the event. Could you just, what would you consider, the best practices for, when you're in the practice field and you're running for a while? Obviously, I think there's some general truths, don't run until brown out, but are there any other additional tips that you would say for that kind of scenario?
The question is there anything that I'd recommend doing differently when using batteries for practice, or maybe code development, or on the practice field, that type of thing? I would actually recommend running a different set of batteries. The problem, or I guess what can happen sometimes is, we all forget. The two batteries that I brought today, I ran those things down last night to 9.8 volts, that kind of thing. People forget. It's fine. I would swap them out. So basically, if you're on the practice field, if you're doing software development, something like that, have a set of 4 or 6 batteries that are designated specifically for essentially, the deep discharge style of I guess running or operating the robot. If you're running practice matches, it's probably actual practice matches where you're driving around a lot and kind of maneuvering, that kind of thing. It's probably safe to use the competition batteries. That's fine. Really, where you run into trouble is if the robot sits on and idle and it just sits there and discharges itself over a couple of hours. Once you hit 9 volts or so, 8 volts, that is, way less than the 50% that's recommended to keep batteries at. Yeah, question?
Why is 9 volts 50% of 12 volts?
The question is, why is 9 volts 50% of 12 volts? No, it's not voltage, it's capacity, energy capacity. That's the trick, right? It's, once again, it's hard to say. It varies by battery. It varies by battery capacity. Manufacturers have different internal rules. It's hard to kind of say, like, at this voltage stop or whatever. The goal here is to prevent the batteries from seeing very deep, slow discharge. These batteries, because they're motorcycle batteries, they are designed to, like, start a motorcycle, to crank a motorcycle. So, like, it's actually okay to continuously hammer them like we do on our robots, right? Like, discharge them using a lot of peaks and draw instantaneous power from them. That's totally okay. And they're also designed for deep discharge. It's just, if you push them beyond where they're comfortable operating, you eat into their usable lifespan. Yeah, and once again, there's the competition batteries. What we used to do is we would take essentially a milk crate, which fits, I think, 5 batteries or so. If you want to stay below, like, the OSHA guidelines for what a single person can lift, 4 batteries is the maximum, because it's the limit is 80 pounds. Yeah, if you take just a milk crate with batteries for the software team to use, that actually will save a lot of trouble. And think about it logistically, right? Hey, we've got a match. Okay, you swap the battery, and you have your software development batteries, right? So as soon as they come back, you know that you already have the battery that you're going to use to put into the robot, right? You don't have to pull from the set, and you don't have to do the queue, or any of that, right? Yeah. Any other questions, or I don't know. Any questions from the chat? I don't know.
We have one comment more than a question.
Oh, okay.
Just simple. I'm not sure why the Andymark battery mount doesn't come with foam, or at least a recommendation to use it.
Mount
The battery mount that Andymark sells.
Oh, I see. Interesting. Yeah, I don't know. I mean, I could text somebody if we wanted to, but I don't know. But yeah, that's, at a high level, what I recommend, and for, handling batteries, what I recommend doing with them, how I have, done stuff at competitions. One last thing. Name your batteries. So name your batteries, like, don't just use, like, A1 and B1 and then so once again, what we used to do is we used to pick a theme, and that, based on the theme, you would know what vintage the battery was. So one year it was, Harry Potter universe characters. Another year was 90s rappers. The year before that was, I don't remember. Like, you pick a theme, right? And you can say, oh, that says Harry Potter in it. That battery's from 2020. Like, you can figure that stuff out pretty quickly. It helps keep track of them. You can keep a spreadsheet, that type of thing. If you can, buy the batteries wholesale. The reason for that is, usually if you buy them wholesale, they will have seen less shipping. If you, honestly, like, try to find a sponsor, like, and find your local Interstate or Batteries Plus or whoever, or, there are MK batteries distributors as well, that you can actually get in touch with. They'll usually either sell you the batteries really, really cheap, or they'll give them to you. These batteries will not have been shipped, right? So if you buy a battery or a pair of batteries from AndyMark, they have to ship them to Indiana, and then they have to give them to UPS, and then UPS will, like, chuck them off of a truck or whatever, right? What we used to do, I used to live in North Carolina, I actually once a year would drive to Raleigh. MK Batteries had a distributor, they had an office actually in Raleigh, and I used to just drive over there, and they'd pull up a pallet of batteries, and we'd load them into the car. So I'd buy 12 batteries, 15 batteries, and drive back to Greensboro. And I think we paid like $15 a battery or something. Like it was actually like a super good deal. Yeah. um, so, yeah, question.
And then I believe we've had to we've been told to break in our batteries before, use them some amount before using them at an event. Is that good practice?
Um, it's hard to say. Oh yes. Yeah, is breaking in the batteries necessary? And is it good practice? I would say, it's probably not a bad idea to get a feel for how the batteries perform. So, in breaking the battery in, you're also understanding what the limits of the battery are, right? So, you're essentially load testing the battery, right? So it's probably not a bad idea. I don't know whether effectiveness improves or doesn't. What is fact is the act of, or I guess the act of consuming the batteries, the energy inside of the battery, and recharging it. If the battery, odds are a new battery has been sitting on a shelf or in a warehouse for a couple of months, and what you're doing is you're breaking apart the sulfation that we talked about when you plug it into the charger. You can't the charger won't charge unless you consume the energy from the battery, but you're probably breaking apart whatever sulfation has already occurred. That's probably the breaking in that you're seeing, right? So, question?
Do you recommend like systems checking on your battery that you're going to play the match with? Especially if you're, I mean, if you're already load testing it, or would you say that you have a different battery set aside for systems check specifically, or what do you recommend? Like, how would systems check fit into the queue?
Yeah, the question is, how would system checks fit into the queue? Would I recommend using the battery you're going to play the match with? Or, would I recommend having an extra battery or something different to test with? Yeah.
Just came back from your match.
Yeah, I would recommend, doing system checks with the battery that you want to use in a match. Because essentially, I mean, another thing you really want to do is zip tie the battery connector, because boy, that is really cheap insurance. And bonus points, if your battery gets knocked out of your robot and it's, sliding around, if it's not a hazard, I won't disable your robot. And because the battery connector is zip tied together, that thing isn't coming apart. So, but yeah, the reason for that is it's part of the procedure, right? It's like, okay, you remove the battery that just came off of, from a match or whatever, right? You put the new fresh one in, you zip tie the connector, and now you know that you're ready for the next match, right? Essentially, it's locked in, and you can do all of the testing and everything else with it. The energy that you consume, like enabling the robot and doing all that, like it's very, very minimal. And what we talked about as well, if it's a charged battery, it's ready to go, the voltages and everything look good. The robot sitting idle for 5 or 10 minutes isn't gonna do anything, right? It won't matter. Yeah, and I don't think that you're being able to quantify hey, yeah, we would have had these extra joules of energy, we would have won the match, or if you can quantify that, I'd love to see it. Yeah. Any other questions? I guess.
Would you show us how to use your battery load tester?
Load tester? Yeah. I mean, yeah, if you want to grab the load tester.
Alright, now we're going to get funky. We're going to get this camera, move it around.
I mean, I can my hands are cold, so like it's really nice to hold. It's just like, but yeah, like it's just nobody, like you said, you know, we've been using this battery since 2001, and like nobody how to take care of the batteries, right?
It's true.
Yeah.
Well, it's all just sort of been best practices based on like what's kind of worked
Mm-hmm.
and
Yeah.
association. It's like this makes sense,
Right.
but it's very hard. It's hard to like provably say this is what broke the battery.
Right.
This is what kept the battery like happy.
Mm-hmm.
So can you go over that battery test
The
again?
battery tester thing again? Yeah.
Just so
Sure.
that we get audio.
So if I know where I need to keep it, I can also. Yeah, there we go. Yeah. Okay. Cool. All right. Yeah. So, like I mentioned, I've modified this battery. You know, really low cost battery tester. I guess this way. Okay. To just have an SB50 to make it really easy and safe to connect to things, because you know if you try to do this with the alligator clips, it's just not going to be effective. But essentially, the way you test this is you'll see a battery voltage and idle voltage when this is you know when it's sitting just connected without turning the charger on or the battery tester on. Excuse me. Flipping the switch will actually just connect some wire. Honestly, it's literally a resistor to this charger, and it'll give you an idea of what the current consumption, or excuse me, what the battery voltage is, and it kind of gives you an idea of what the current capacity of the battery is at that time. It's not going to be exact. These testers are typically configured for, or you know, the scale on this graph is typically configured for like larger batteries. You might be able to find like a motorcycle, yeah, like your standard car battery, whatever. Right? You might be able to find like a motorcycle version of this. But roughly, like once you understand, oh, okay, a good battery test, you know, like we saw earlier, like 400 to 600 amps on this scale, you know, that might be enough. But yeah, basically you want to load test the battery for, you know, 3 to 5 seconds or so. We'll do 3. Yeah. 1 Mississippi, 2 Mississippi, 3 Mississippi. Did you get a glimpse of what that was? Kind of.
At 600, I think it looked like 400, but I
400?
also didn't have a great.
Yeah, great view of it. Yeah. So yeah, it looked like, you know, about 400 amps. I guess once again, it's hard to say. The best thing to do is for your batteries and your charger, or so your batteries and your tester, you'll want to get an idea for like, hey, this is what a really good battery was. We just ran it on the robot. It did well. You know, recharge the battery and then load test it to get an idea of what the limit should be for your tester, right? But that's pretty much all there is to it, right? Don't be alarmed if you see like smoke, a little bit of smoke, or you know, like little or like it gets warm or whatever. Like it literally is connecting a resistor across the battery, and like it will get really hot. But
So what's the threshold for smoke?
if it like persists for more than a couple of seconds, you know, see your doctor. I mean, you know, stop it, right? But yeah, that's about it.
There is a question.
Yeah.
2 questions. We'll get to that first one. Is there a reason you are using a jumper between the battery leads and the battery tester leads?
Yes. Yes. So I have. So the question is there a reason that I'm using a jumper, which is this thing, between my battery and my tester? This is just an adapter to go from an SB120 to an SB50. You know, I keep these around because the batteries that I have and that I brought have SB120s. However, you know, the all of Jack's batteries run on SB50s.
The majority of teams
Yeah, the majority of teams still run on SP50s.
I mean, they come in the kit.
Yeah, that's pretty much it, just to make everything compatible.
Yeah, this is 50 amps, this is 120.
Yeah. Well, peak.
Whatever, it's just what it says on the thing. What do
I
you
know.
want from me?
It's peak versus RMS. I mean, we can talk about like, what root mean squared means and what, how it affects the.
Go back to your Ohm's alleged law.
I mean, that's for later. But yeah, there's I don't know. There are a lot of things that also happen, or a lot of telemetry that I think we're missing. The bandwidth of, talk about bandwidth, right? The bandwidth, in other words, the frequency that you can log data, I think last time I looked at it is probably limited to like 50 hertz or 100 hertz, maybe. I don't know what the voltage logging frequency is. But it's significantly lower than what the peak voltages you get or you see on a robot are. The other thing to keep in mind is when you use brake mode, for example, there's a little bit of a regenerative process that happens, and you can actually, I think the highest I've seen was like 40 something volts on the robot bus. But the only way to see it is with an oscilloscope or with a high speed DAC. So there's a lot of other stuff that, like, we tend to think, oh yeah, Ohm's law. Yeah, I'm only, I'm at 12 point whatever volts or 13 volts, and I'm only drawing, according to the PH or PDP, 50 amps. It's like, no, you're not. But yeah, that's a discussion for another day, I guess.
He was talking about how often the battery voltage gets sampled in logs.
I don't know.
Yeah,
That's why.
I'm pretty sure, like, it's with the old PDP, it used to be like 10 hertz. Like, it used to be like woefully low. I think things have changed since then. I'm not sure. But yeah. Oh.
What is the, like, when should we stop using the battery when it reads low enough on the tester?
So the question is, like, when, what's the threshold, or when should you stop using a battery? So do you mean load test wise, or, okay, on the load tester, probably anything below, like, okay, it depends on your robot. I think that's probably the right answer. It depends on the robot. The little robot that I brought that is just a little test vehicle, it's probably more than sufficient to run, one of these old batteries that, can only, when load tested, only shows that it'll do 200 amps or something. If we were to put this battery into a full-size competition robot, you'd probably maybe get, a minute and a half, 2 minutes of driving around. So the more correct answer is it depends on how big and how heavy your robot is, and what your drivetrain is, and like all that stuff. As far as what is acceptable and what is not, where the limit is, my recommendation is sample the batteries that you have and work with your drivers to figure out like what is good for them, what feels good for them, and what feels bad for them. Try to make it a little bit of a blind study, like, you load test everything, get the numbers, but don't tell them, and then just like hand off the battery to them and say, play with this one, play with this one. And once they come back with, I like this battery, then you set your limit. That's probably the right way to do it. Yeah.
But then after they're below that threshold, you just have to recycle.
No, you give them to the programmers. No, like literally, that you start using them for stuff like that. Use them for on the practice field. Give them to the programmers. That type of thing. If you take the batteries to O'Reilly's will give you, even if you never bought the battery from them, for every battery that you return, they'll give you like a $25 gift card, something like that.
Like we've done
Yeah.
recycling. We've gone through more than one set of batteries.
Oh yeah. Like I've probably given O'Reilly like over 16 years, probably like 50 batteries or something. Like, it's a lot.
So we do have another question, which is kind of going back a little bit, but at what voltage or at what point
should you swap batteries on the robot during practice or programming during autos? Is it when browning out occurs or some other time?
The question is like, at what point should we, or I guess, at what point should you, I guess, stop using battery when working on autos or, you know, kind of doing any development work, maybe. Certainly before like the Rio says, you know, brown out and is complaining or whatever, like way before that. You know, once again, it gets a little bit complicated to put a specific number on it because if the robot's tiny, then you're not consuming a lot of current when moving around. If the robot's big, then different story, right? Probably, if you want to be safe, probably when it shows about, you know, 12.2 volts or so, when it's idle. Yeah,
Well,
I see the
because there are
faces.
different levels of code development. Like you
Right.
might be doing a long-term series of things where you're changing set points
Mm-hmm.
and you're running a couple of motors at a time.
Right.
But if you're doing like auto testing, a lot of autos currently, like auto starts and you start running 20 motors at once.
Right.
And like you're going to be doing like the worst thing you can, well, not the worst thing you can do with a battery, but you're going to be asking a lot of it almost immediately. So you'll
Right.
see very different battery performances.
Right. Yeah, I hate to kind of like, you know,
Give a number.
yeah, well, it's like, actually, it's the other way around. I hate to kind of say, well, you know, it depends for everything, but like, really it is, you've got to look at the scenario, right? At the end of the day, the battery does not like to be discharged, you know, more than 50% of its capacity. Capacity doesn't necessarily equal voltage. That's the problem. That's why we need the load tester. Capacity doesn't equal voltage, right? We're talking about total energy inside of the battery, or potential inside of the battery, which is, you know, hard to quantify sometimes. Yeah. Any other questions in the chat, or I don't know. Yeah, but I mean, 12 point. If you like had to pick a number, I think like 12.2, 12. It's probably like pretty good. It's a good threshold. Which I see some of the software team over here like, oh, what?
We definitely, I mean,
I've done that too, right? Like I said, this thing was at like, you know, high 9 yesterday. Like,
Well, I don't know. It's like, I don't know.
yeah, we've definitely, we've consistently run them in the 11s, or like you do a practice session, not coding wise, but
Mhm.
you're doing like, instead of a match, you're running it for like 4 or 5 minutes, and then you're just.
here's a thought. Look at the voltage of the battery when it comes off of a match, and don't go lower than that. That's probably a really nice way to do it. Which, I mean, batteries, if I had to guess, probably come off at like 11.8, 11.9-ish.
Yeah, but it would definitely
It
depend
depends,
on
but
your
yeah.
robot, but that would be, I mean, you could do it by, you could practice the way that you play and like set the timer and not run past that, or you could say our threshold is based on, like, we're not going to be running a battery that's
Mhm.
lower than this, so
Right.
let's not run batteries that are lower than this.
That's probably actually a really good way to do it. Think about it. But yeah, I hope this was useful. I hope it was useful. I hope that folks benefit from it. And yeah, if there are any questions, I mean, we can. You probably find me on Chief and wherever else. So
Yeah, there will be ways to
Yes.
communicate questions.
Yeah.
On this video or elsewhere.
Sweet.
We or Juan can go over like whatever it is.
Yeah.
You brought a lot of stuff. You
I
wanna show
did.
any of them?
Oh, I mean,
We do have
yeah.
one more question. You said that voltage isn't indicative of the battery's capacity. So what actually is? For example, we have a CTRE battery Beak that we use to look at internal resistance and sort batteries based on that.
Yeah, so that's a deep question. All right, so let's buckle in, everybody.
And can
So-
you repeat the question? Just
Yeah, sure. So the question is, so if battery voltage is not indicative of total energy in the battery, what is? And unfortunately, it's hard to say because the battery, electrically, the battery also has a very, very small resistor inside of it. Like you can think of it electrically as, it is an energy source plus a resistor. And the value of the resistor changes as you consume energy from the battery. So the battery's efficiency changes as you use the battery. So unfortunately, it's not a single number, it's a moving target. That's actually why the battery beak will give you it'll give you a resistance reading, right? An internal resistance estimate or measurement. And that's also why that measurement changes based upon how soon it was on the charger. Like you can trick this thing into thinking that a battery is better than what it is if you immediately pull it off the charger and plug it in and test it. You can do that. The way that the battery beak works is there is a very low resistance but very precise resistor inside of the battery beak. It is meant to load test, and I say that with air quotes. Turn it around so that it's easy.
We're gonna be able to see that no matter what we do.
0.061. All right, 0.061 and V2, 11.8 volts at 18 amps. So what we're gonna do? So somebody remember those numbers in chat.
Wait, say it again.
0.062 and 11.8. Somebody remember that. And we're gonna wait a couple of minutes and then we'll come back and measure it. Basically, the way that the battery beak works is it attempts to do what this load tester does. It has a very precise resistor inside of it, and it's a very precise but very low resistance resistor inside of it. It attempts to consume current, pull current out of the battery. The problem is that, and that's how you get the 3 voltage measurement, right? The problem is that the measurement time is very, very short because it's a very small resistor, right? The reason that this thing has to be so big is because, it's, it gets really hot. So what that means is the measurement you can't really use it for reliability testing, load testing, because you're not consuming enough current for long enough, right? It's the 3 seconds, 5 seconds that will actually get you a very accurate measurement of reliability. As far as total energy inside of the battery, it is probably pretty good at estimating it, but it's still an estimate. The reality is we consume a lot of current we pull a lot of current out of the battery when we use it, and you can't estimate that because the efficiency and the ability to pull power out of the battery changes as the battery heats up. So then there's a percentage that is used for work to drive your robot, and there's a percentage that's lost as heat. That's why testing under a load, a real load, will give you a good estimate of how stable that consumption is. I've actually seen a battery that was so bad, you'd measure it and it was, 12.9, 13 volts. But as soon as you started drawing current from it, you just watch that voltage meter, the needle, basically very quickly start walking down. And at the end of the test, they were, that battery was at 11 point something. You went from 13 to 11.5 volts or so. So it's, I don't know if that directly answered your question, but it's it's hard to estimate, which is why having a feel for how the battery performs under load is important.
So almost a follow-up question, but from a different person.
Yeah.
Is another solution for determining battery capacity, I assume, check the driver station logs for a practice match and sum the total current and use that for benchmarks of development versus competition batteries for like when compared to the measurements from the battery tester?
Ooh, this is a peak versus RMS question. So the question is, can you basically look at the logs in the driver station logs, look at how much current was consumed during a match, and basically use that to assess the total energy of the in the battery. So yes and no. It will depend on what we were talking about earlier, right? The measurement capabilities of the FRC system are pretty limited. I'm not sure what the frequency is, but if the frequency is very the logging frequency is very low, the data acquisition only looks at a peak value at one point in time. The problem is that there's a lot more that goes on, between those samples, right? You would need to have, in order to like get a really good feel for what the current consumption was, you would need to log at a much higher frequency and then essentially add up all of those points, right? You essentially don't have enough resolution to be able to see all of the smaller changes. So you may, instead of it being a peak that occurs, that spikes to 100 amps, you may see a point at 30 amps and you may see a point at 20 amps because you don't have enough resolution to see that. However, having said that, it won't give you an absolute measurement, but once again, you can draw some correlation from it, right? It is still good, it is a good practice to keep track of changes or differences between that battery. As long as you don't try to compare the performance of this battery versus that battery, it's probably okay. If you basically take those measurements and you do all that math and you know that, hey, this was, I don't know, whatever, Shinji, got it.
Get in the robot, Shinji.
Oh boy. So if you look at, Shinji or whatever, you can tell that, okay, hey, listen, this battery, we've seen that this battery on a typical match, whatever, like what I was mentioning earlier, it started at this voltage, it ended at this voltage, the logs show that we consumed this much power. All of a sudden, you leave a match and you see that change, suddenly it's like, whoa, we ended, 0.3 volts lower than where we normally are. Whoa, we didn't consume more current, just the battery gave us less power. Then you know that battery is probably toast. In that sense, it is a good approach, but it's only valid within the same battery.
The fact that we can't directly measure what we're trying to measure makes me think that this whole presentation could have just been try to keep the magic juice happy.
Yep, that is literally what it is. Well, okay, in this
Batteries
case,
are
it's
filled with magic juice. They get sad.
Yep.
Don't make the batteries sad.
Yeah. What's even funnier? It's like technically Gatorade with like a little bit, a smidge of acid. Is
Does
really
Gatorade
hyper.
have acid in it?
It has salt in it.
Okay.
Yeah, exactly. Yes, Gatorade, that's exactly what it is. Hey, it also turns out that our bodies need electrolytes in order to function.
Measure
Yeah.
changes.
It's like, all right, we're
We're off the deep end here.
Yeah. Well, it changed a little, but we lost 0.2 volts at 18 amps.
What's it read?
11.6 volts at 18 amps, and the resistance did seem to stay pretty stable, so 0.062. So it did increase a little bit. So that's kind of the problem, right? Unless you actually test the battery in how you, I don't want to say directly how you would use it, but you need to really exercise the battery to get a good idea for what's going on with it. I mean, improvements to this thing, if somebody wants to make a drop-in replacement that's digital and has if somebody wants to make a plot or whatever, or make put an Arduino in this thing and do limits and have it do peak and all that stuff, definitely let me know. I'm happy to figure this out because like that would be pretty sick.
Okay, the students are huddled and I want to know.
Uh-oh.
Well, that resistance is like 6 times higher than it normally is.
Yeah.
So
Ain't that a pickle?
they're reporting that the
Yeah, the
we usually
resistance is a
don't
lot
see
higher.
resistance that high by factors.
Really?
Yeah, it's normally
That's not the one that we load tested though.
It's not.
You wanna give
Oh,
her a
let me-
go?
Let me get, so yeah.
No, yeah. Let's give
So
her.
get
Let's,
the pigtail.
yeah. Let's actually no pigtail. Eat it first.
Oh, yeah.
So
So the highest they've seen on these batteries before this point is 2.1, not 6.1.
so yeah. Like so we tested a good battery, and like I won't be able to tell because I'm holding it and looking at it sideways. But like
you get head on
yeah,
this
somebody needs to look at it head on to tell.
without blocking the camera.
Ready?
So
It is gonna.
these steps, the needle on that
Yeah.
one is going to
So it'll change. So ready? All right. What? Oh, yeah. No, she's dead, Jim. Oh, she's really dead, Jim. No, like it's gone.
Oh,
So
Yeah.
throw this away.
yeah.
Yeah, but like, there you go.
Like this gave us a set of numbers that
Mhm.
was like, oh, slightly worrisome, and that said,
This is like it is like get rid of it. No, like
It wasn't in the
it was
range.
it was like in bad, and it just like
Yeah.
kept going down. Yeah, so like this is like garbage now. There you go. We did not skip this, folks. We promise. This actually happened.
yeah, we don't keep that good track of our batteries, so I couldn't have done that.
I guess one other thing to mention is I'd have to send you all the link. We can send it to folks or whatever. But a couple years ago, we actually load tested every battery in our library. I borrowed like a 200 amp digital load tester from work, and all those files are on GitHub. So like if somebody wanted to go and see what that looks like when you're drawing like 30 amps or 50 amps continuous from a battery, like that'd be I can send that. Yeah, and I'm talking like 30 batteries. Like it's not like, one or two. Like it's actually a big library of them, different manufacturers and everything.
What's the TV thing?
Oh, the oscilloscope.
Oh, that's an oscilloscope. So one of the things I wanted to look at is when you plug a battery into a charger, we can actually watch what the charger does to the battery.
Oh, interesting.
Yeah, that's why I brought it. Yeah.
It's got a little TV.
There's a little TV screen.
I mean, we can, if you want to play with that, we can do that too.
Let's play with the oscilloscope.
We can play with the oscilloscope.
I think we have to roll over. Let's have to sort this. Oh, I want to. Oh,
I'm gonna say bad.
Oh yeah, we will the battery.
Roll the battery turnover.
yeah. It does roll.
It does.
So we're gonna roll the battery card over. We've got an oscilloscope that Juan's gonna play with, and the kids have assured me that we will label Shinji with a label that says "bad question mark," which is the
Not a question mark.
no. Bad question mark is the only way to label a battery that you know is dead.
No, you know what I would normally do? I would take that battery that I knew for a fact to be dead, and I would immediately wire cut the leads off and put it in the back of my car. Like just you remove it from the equation.
Yeah, no, we typically get the label maker out. Bad question mark.
Yeah.
That's how you know something happened.
Yep.
At some point.
Bad question mark is it performed badly in one match, or if we dropped it or something.
It could be anything. It's like the question mark.
I mean, have I had the cost, I guess the opportunity cost discussion with you all?
We've addressed opportunity cost to some degree with not. I don't use match dollars because that is not a framework that makes sense to me. But in the sense that like you can't lose any match. So how much effort you put into not losing a match for reasons that are outside of like how you perform.
Right.
How like the variance of match strategy and how robots do. But instead your battery died because you weren't prepared enough. Like you can never do that. So
Right.
there's no amount of effort that isn't worth it, which is frustrating.
It's true. Yeah, it's tough. Let's see. Don't drop the camera. We get two terminals in one of these. Oh yeah, the other thing is for the battery naming thing, never name them team like students.
Students on the team.
Yeah, never name them students or mentors.
Oh yeah, we definitely don't have that.
Yeah.
That's a student that was formerly on the team.
No, never name them anybody that you know personally. The reason for that is because it's an implicit bias thing. You will like
You'll have associations
with the name, and it's just as a. I used to be lead mentor, so it's the thing I
We have
learned.
successfully made it through an entire season without naming our robot after somebody who was on the team.
Ah, wonderful.
I'm hoping to continue that trend.
I need one that is not shrink wrapped quite as nice.
It gotta be named
Give
after
me the.
I mean, like the only thing we can do is just start to do it because we actually. I mean, you can get to the terminal on this one.
Okay. Yeah, I actually need to get to both, unfortunately. I think I can probably get into that one.
We got knives.
We got knives.
I'm sorry, our terminals are well insulated.
Hey, listen. This is why I don't robot inspect. Did you say Cake Monster Mash? Oh, wait, that
Don't
was
just
just
repeat
wrong.
everything.
Why not?
Because we're live.
Oh, it's gonna be great.
Context matters.
Wait, what? Oh, yeah. Okay,
So-
got it. Yep. Understood.
One positive, our battery leads are well insulated because he's trying to get to them right now.
They're less well insulated. No, they're less well insulated this year, I think, right? We changed how we did them from this.
Well, this battery's from
I mean,
20.
it changes every time you do something, but
Yeah.
Like different material.
yeah, this heat shrink is
Yeah,
preposterous.
that's that heat shrink is quite something.
It's structural.
It is.
All right. The reason I need to get to the bottom of the battery is because the connector, the charger's gonna wind up here. So.
He's trying to connect to the
Jeez.
You trick we need to like.
This heat shrink is something.
We needed to shield the battery from the heat gun that we were using, or else it like melts the top of the battery.
Yeah.
It's good stuff.
Like you could. I mean, I think if you like expose this to salt water, it'd probably be okay. My goodness.
Marine batteries.
You talk about like marine grade stuff, jeez. By the way, marine. I guess that's another. We can talk about batteries while we're here. Marine grade batteries are designed for low power, low current consumption. They're actually that's why they're deep discharge. That does nothing to the way that FRC uses batteries. Because deep discharge batteries are actually meant so that like when you're on a boat and you're like in the port, like or near docks or whatever, you're trolling around. That's just a low current load. So they do nothing for FRC because, like we discussed, FRC is very spiky current consumption. Come on. Oh, this battery's already dead, right?
Yes.
You're not supposed to do this. Actually, I can show you why. See what I just did there?
Oh yeah.
I just cracked the
Top
case.
of the case.
But I put a little bit on it, but that wasn't like.
It's like a person.
Yeah.
Robots do more.
Yeah.
Can do more damage.
So that's actually why you don't do that. I mean, it's
Shinji.
Everybody's like, wait, what?
Juan just broke our battery.
Yeah, it's like, this guy just came in here and just like completely destroyed. I'm just gonna hold this back, whatever.
I'd apologize, but I'm not sorry.
It's fine.
This is like you're not
Never
supposed to be able to attach to it.
Yeah, like it's doing the thing. All right. So I need to just configure the. I just need to configure the oscilloscope real quick.
This is like those labs in high school that you
Yeah.
don't understand, but you get to turn knobs.
Yeah.
We
Alright,
did
that's
this
fine.
in some sense.
We didn't understand.
Yeah, we did.
Turn
We
on-
understood that.
It also has a touch screen, which is kind of nice. This is the personal one, by the way. I didn't actually borrow this from Mark. Format. We'll see what we see at 2 volts per division. What I'm going to do is I'm going to set this to AC because I don't want to deal with the DC. Alright. And I need to set up my trigger. We'll set up normal trigger mode. Set up the trigger, edge is C1. Yep, that's good. And my voltage level, I wanted to trigger at there. That probably will be okay. Can you plug in the battery for me? Okay. That. Okay, so the spike that we saw when the charger connected was higher than that. All right. Can you unplug it and then plug it back in? No, I missed it. All right. The thing is, I don't know exactly what it'll look like, so I'm trying to find the pulse. All right. No, still missed it. I promise this will make sense once we actually catch one. All right. All right. Yeah, if you want to do, yeah, go ahead and try that. Ready?
Yeah.
Okay. So that tells me that this is just what the connecting the connector looks like. I'm trying to catch what the charger is doing. It probably takes a little bit. All right.
Yeah, because it should be this one. It says it's charging now.
Can you let's do it, or can you unplug it one more time and plug it back in? I'm like really expanding the time base here.
You might want to try changing that charger because that one might be broken.
You think it's a charger?
Yeah, like half of those are broken.
I swear it's not that many.
No, it is that many.
It's not that many.
Yeah.
Oh yeah, there we go. Well,
It's not plugged into anything.
no, I know it's not. It's the so what it's doing is it's sampling. It takes time to sample.
Okay.
Right. That gave me an idea of what we're looking for. All right. Yeah, ready. Okay. It's acquiring the data, so we're gonna just let it sit. Did you do it? All right. One more time, I promise. Come on, buddy, do it. It did it earlier. Like you could actually see some of the switching. Yeah, because if I like really zoom in here, it did do it before. 500 a millisecond. All right, let's do 200. Like I said, I'm kind of guessing because I don't know exactly what the pulse would look like. All right, and we'll do single shot. All right. there's really not. No. Dang it! I thought this was gonna be like easy. No.
The FRC story.
I know. Tell me about it. I don't know. We can keep messing with it. We can. You all tell me.
What do you? I don't know. What's it supposed to be?
So
Or, like-
basically, I don't know if you all saw the square wave, all the switching and everything. Basically, it's the process that I was telling you all earlier. Where it tries to like break apart the crystals. That's actually like what it, like all those square waves is actually what this would look like. So like it was just more than anything to see it. But I don't know. Y'all tell me. Does this one say that it's? Yeah, I guess it says it's charging or whatever. Yeah.
I think it's,
Charging. Yeah, I don't know. I can try and like take some screenshots of the one that I have at home. I don't know.
Yeah. Okay.
Either way, it was meant to be to try and get a cool picture of it, or video or shot of it. Other things that we can do is we can look at current. If you all wanted to look at current on like motor controllers, if you all wanted to like run things, I brought a thermal. Like I brought all the tools, so like there's a thermal camera and stuff as well. You know. Or we could look at the Quest headset on the robot.
That might be outside the scope of this, but like if we ran our 2K23, it's not like a huge. That one's not a huge battery hog because it's especially since one of the modules doesn't. Just like without draining it, will we see anything in the thermal space without running stuff?
It'll be interesting to kind of like see the motors heat up, and actually you can check the cables as well. Cable runs, the PDH, whatever you all have on it. PDH, yeah. It's the thermal camera is really handy to detect loose cables on the PDH, or anything where like you're clamping the sheathing, or like you didn't strip the cable long enough, or something like that. Like it's actually really handy for finding issues like that. In particular, on the PDH, the main battery leads they're notorious for like not having enough cable stripped, and you wind up making a hot spot, and that's usually why most of these things melt. But like whenever they do, that's why usually. But yeah.
Yeah, I don't have anything particular.
Yeah.
Do you have anything?
Unless y'all want to see anything else, but. Yeah. Check the chat.
There are no other questions in the chat.
Okay.
But I think we can close out then.
Yeah. Yeah.
Nice note to end on.
Yeah. But yeah. No, if I hope this was helpful. Some of it was rambling, I know, but like always happy to chat about stuff, and if anybody has questions, let me know. Yeah, that was the rest of them. It was just like Ohm's law and how to measure stuff and that kind of thing. And I also wanted to get into discussions of like how do you measure current when it's that much current, right? There are ways to do it, because you can't if you put a multimeter in series with a motor controller, like the fuse in that thing is gone. So, but yeah. Hope it was helpful, and hope you all learned. You all learned something. Yeah. So treat your batteries with love and care.
Or they'll end up like shit.
Yeah, or they'll end up like shit.
Or Juan will come by and crack your battery case one by one.
I've got some bolt cutters. I can put them in the car for the competition, and we can take care of some batteries.
Okay. On that note, thank you for watching, and good night.
Good night, or good afternoon, even though it looks like night here, but whatever.
I go by the Daystar.
Oh, fair.